All right, everybody, welcome to 16.2, which is entitled The Wave Nature of Light. So we're going to be talking primarily about color, what gives light its color, diffraction, which is the bending of a wave around a barrier. I've got some really interesting visualizations to show you why shadows aren't usually very crisp. Color, the visible spectrum, adding light together. What happens if we add red light to green light? Paint, colors by subtraction. What happens if we combine yellow paint with cyan paint? And then finally, what happens if we start shining different colored light on different colored objects? For instance, this middle one, you'll see that there is red light being shown on different colored dye. All right, so the wave nature of light. Light is a wave. Now, it's not a longitudinal wave like we're used to, or a transverse wave. It's an electromagnetic wave. What it is you take an electric field and you jiggle it in a circle, and what that does is that creates a magnetic field. And then that magnetic field creates an electric field in the opposite way, and that opposite electric field will create an opposite magnetic field, and then that opposite magnetic field will create, and then this is the electromagnetic spectrum. Well, it's an electromagnetic wave. And then this series, where one wave creates the next, this series propagates out at the speed of light, which is 299,792,458 meters per second. So we call this a wave. And this distance right here, we call it a wavelength. So what we're going to see, you're going to see a bunch of pictures that look like this, representing waves, but that's truly not what they are. They are a jiggling in the electromagnetic field. Electricity creates magnetism. Magnetism creates electricity. Now, color. What color is, it's just a definition of frequency or wavelength. You'll notice down here that red has a very long wavelength as compared to blue at the top, violet, Roy G. Biv. Violet's got a very short wavelength. You can barely see this. It's a very short wavelength compared to red. The human eye sees from approximately 400 nanometers to 700 nanometers. That's the bandwidth. The entire visible spectrum exists between these two numbers, between these two wavelengths. These are all that the human eye can see. There is stuff above what we can see or below what we can see, depending upon. There are things below red, which we call infrared, as there are things above what we can see. Above meaning ultraviolet. Anything ultraviolet, and then we've got different specifications for different bandwidths, because where do radio waves start and infrared waves end? Where does X-rays begin and ultraviolet cease? Now, diffraction. What diffraction is waves bending when they go around a corner. I found a really interesting animation here. This is an animation that shows waves coming into and approaching a slit. So you'll see waves approaching, and they're relatively straight, but when they approach that slit, they bend around the corner. This bending is what we call diffraction. Now, you can make a small slit. We can make a medium-sized slit. Watch the differences. Or we can make a large slit. Over here, we can do the same thing where we can adjust the gap size to be very large or be very small. Notice as the gap size equals the wavelength, the diffraction increases, so the wave spreads out more. Down here, what if we start adding 2 slits for this to go through? Down here, this is really interesting. Here we'll just do 1 slit, and you'll see the wave pattern going out here. We'll do the other one. But what happens if you have 2 slits for the waves to be passing through? You're going to notice that this one and then you have this one. And what you're going to see is a pattern of where these waves cross we have interference patterns. And this is literally what happens if we were to show laser light, which is coherent light. You would see an interference pattern. This is diffraction. So unlike waves going straight in, they actually bend around corners because of diffraction. Now, as I mentioned before, color is just another way to say wavelength. So each color, violet 400, blue 450, cyan 500, green, yellow, orange, and red, 400 to 700. Every color has its own. You don't have to memorize this, but you do have to know that we go from 400 nanometers up to 700 nanometers. That's the visible spectrum. Now, colors by addition. What happens if we combine red light with green light? When you combine red light with green light, you get yellow. When you combine green with blue, you get cyan, and red with blue, you get magenta. Now, we call red, blue, and green the primary colors. Red, blue, and green are the primary colors. If we add any 2 of these, we get the secondary colors. Now, adding red plus blue plus green together, you get white. Now, this is only when we add colors of light together. Adding colors of paint, that's different. Complementary colors are any 2 colors that you add together to make white. So for instance, if you take blue light and you add it with yellow light, because you know that yellow is also red and green. So blue plus red plus green is equal to white. Or, so the complementary colors, blue and yellow, green and magenta, red and cyan. Now, adding paint together is a little bit different because paints and pigments are absorbers of certain frequencies. For instance, if I had a blue shirt on, and I'm outside in the sun, and we know that the sun gives off all light, which in this case, let's just call all light red, green, and blue. RGB. Now, what blue does is it will reflect the blue light. Well, what does it do to both green and red? Well, it will absorb the green, it will absorb the red, and it will release it as heat. So meaning that it doesn't just disappear, the energy goes out as heat. And the reason that we see a blue shirt is that it's reflecting blue light into our eyes. Now, in the world of paint, this is completely different. The primary colors of paint are cyan, magenta, and yellow. So it's flipped. And the secondary colors are green, blue, and red. Now, what would happen if we mixed yellow and cyan? Correct? So yellow and cyan. Now, what does yellow do? Well, in order for our eyes to see yellow, it has to give us red and green. So that means that it absorbs blue. That's what yellow's doing, right? Back with our light, in order to see yellow, we take red and green, and that's how we see yellow. Now cyan. What is cyan doing? Well, in order for our eyes to see cyan, what it's doing is it's giving us green and blue. What does it absorb? It absorbs the other one, which is red. It absorbs red. Now check this out. You take something that absorbs blue and you combine it with something that absorbs red. Well, what's left? It's going to reflect green. That's the only thing left. That's the common denominator here, green. So yellow plus cyan equals green. So if you look at this up here, notice how we combined yellow and cyan. Yellow and cyan give you green. Cyan, magenta, going through that same process is going to give me blue. Magenta and yellow, same process is going to give me red. We call it color by subtraction because what you're doing, what does it absorb? They're both absorbing certain things. Now, these dye right here, for instance, take a look at this middle page right here. Here you can see the true colors of all the dice. Now, green absorbs red. It absorbs blue, but will reflect green. So when you shine red light on a green dye, this red light hits it and ends. It gets absorbed. That's why it looks black, because the red light is being absorbed. Likewise, that is also why the blue dye looks black. And then look in the blue light. Yellow, like we said before, this dice right here, yellow absorbs blue. Remember, in order for our eyes to see yellow, we need red and green. So imagine shining blue light on something that absorbs blue. That's why this guy looks dark. Painting things, big essential understanding. Combining light and combining paint, they are similar, but they're very different. Combining red and green light makes yellow. Combining red and green paint is not going to give you yellow. This is color by subtraction, looking at what things the colors absorb. Here you're looking at what things the colors emit. So that kind of concludes 16-2, the wave nature of light.